Thank you very much for the organizers for inviting me here. I will start by pointing out that I'm not a geometer. I work on combinatorics and some combination with group theory, Euclidean geometry, so I don't know a lot of things of geometry, but still you are encouraged to ask questions. If I cannot answer, I'm a co-author. So. And the rest of the speakers of the co-authors are Thierry Fulbois, a researcher from Marseille. He works in geometry of infinite groups. Camilo Ramirez, he was over there, he's a PhD student of Iran. And Miguel Draghi was a postdoc of mine who worked in complete combinatorics, no other relationship. So it wasn't a uniform group, it had some variety, and we attacked a problem which has some variety too. We started with a combinatorial problem, and somehow we ended up with an infinite type surface, namely the one called Loch Ness Monster, and I will define everything. Well, I will try, so stop me if I don't. So, first of all, I work on maps on surfaces, but not this kind of maps. Also, I would rather not work with these other maps. These are very hard to work with. I want more structure in the maps, so these are nicer to me. And why do I work with these? Well, they have symmetries. So, for instance, here I have rotational symmetries, or reflections, or well, light reflections, or whichever other symmetry you can find. I also like this map. If you think it as the torus embedded in 3 space, then there's not that much symmetry here. You can only rotate, but still the combinatorial structure allows symmetry that would take me the outside to the inside. So this would be a random model probably of the same map that allows all sorts of things. So properly speaking, now I will define things. A map is a two-cell embedding of a graph on a surface. Two-cell embedding means when I remove the image of the graph, what I'm left are faces that are homeomorphic to disks. So a face cannot have a handle, a face cannot have a hole in the middle, it cannot be disconnected, and so on. Throughout, the surfaces will have no boundary, and they will be orientable, or the theory of maps on surfaces is developed also on non-orientable surfaces. So here is an example of a map on a compact surface. That's a hexagonal grid on the torus, and an example of a map on a non-compact surface. And now, usually I work with automorphisms of the map, which are defined only as bijections of vertices, edges, and faces that preserve the structure. So here I don't require any geometry, but whenever the geometry of the surface is given or is understood, then we talk about symmetry, which are isometries of the surface preserving my map. So it's clear that every symmetry will be an automorphism, but not the other way around. So, for example, in the torus, in the 2 versions of the torus I put at the beginning, in the torus in the left, I would have a lot more automorphisms that cannot be realized by a symmetry, right? Like taking the torus, the outside to the inside. In order to define regular maps, which play a crucial role in this talk, I need to define first a flag. A flag of a map is a triple consisting of a vertex, which is contained on an edge, which is contained on a face. And it can be visualized if I have 2 faces of, well, one face of the map. I can take a triangle that has a vertex on the vertex that I chose, another vertex in the midpoint of the edge I chose, and the third vertex would be in the center of the face I chose, so that creates a triangle. And these flags give me a triangulation of the surface. So for each choice of vertex, edge, and face, I get these triangles, and well, there's a decomposition in flags. And I will say that a map is regular whenever any flag can be taken to any other flag by an automorphism, or by a symmetry, depending on my context. So examples of these regular maps are, of course, the Platonic solids. If they are not regular, then something is wrong. And I think of these as projected to the sphere, right? So they are maps on the sphere. Other examples are the tessellations of the plane by squares, by regular triangles, regular hexagons, or equilateral triangles. And it's known that on each compact topological surface, there is at least one regular map. So there are plenty of those. Now, I also want to introduce the concept of covers, just to be safe, but I guess that you know more than me about this. So to me, a cover of a map will be, well, of course, it's a map on the sphere. It's easier to draw the hexagonal prism here, but think of the sphere. I take a subgroup of the automorphism group of my map. In this case, I'm thinking of the rotation by pi. Although it looks like 2 pi over 3, it's pi. And then what happens is I identify vertices that are in the same orbit, edges that are in the same orbit, faces that are in the same orbit. So what I get is a prism over the triangle, and I can recover everything. So for instance, if I color the vertices in the lower hexagon and put the same color if they are identified by an isometry of my group, then the black vertex can be sent here, the blue vertex there, the yellow vertex there, and all the incidences are preserved. This hexagonal face wraps twice around to go to the triangle and so on. So generally, by a cover, I will understand something like that. It can have branch points. And with maps, we have been concerned recently about regular covers. Here, I have to apologize. I know that there are several concepts called regular covers. One of them is the one I'm going to use here, which means it will be a map, which is regular, and happens to be a cover of another map. So, I'm sorry if some people will get confused, but I didn't invent it. So a minimal regular cover means it will be a regular map, which is a cover of a map, and will be minimal in the sense that any other regular cover covers itself the minimal regular cover. So in particular, if I start with a regular map, it's a cover of itself, it's regular, so it's its own regular cover. And we know since several years ago that every map, it doesn't matter if it's finite or infinite, has a minimal regular cover, and even more, if the map is finite, then we know that the minimal regular cover is finite. So I will give an example. This here is the truncated tetrahedron, again in the sphere. It has 4 hexagonal faces. We can see 3 of them, the other one is at the back. And 4 triangular faces. So that's clearly non-regular. If I take a flag, say in this triangle, and a flag in this hexagon, there will be no symmetry that takes one to the other. And the minimal regular cover is precisely this hexagonal grid in the torus to show that, well, it requires several steps. I will not prove that that's regular, but it is. To prove that it's a cover, we can label the faces. That will give us also the... So what I'm doing is, this face number 1 is the pre-image of this triangle, and it's the only face that wraps twice to come here. Face number 2 has 2 pre-images, and so on. If I want to see the pre-image of this edge, for example, what I have to do is look at all the edges of stairs that are between something level 1 and something level 2, and so on. Vertices, the same thing. And we can see there, with a little bit of patience, that if I start in phase number 1, around I have 2, 3, 4, 2, 3, 4, 2, 3, 4, so everything moves locally well. And it doesn't matter where I start, so with patience you can see that it's a cover, and to see that it's the minimal is also not very hard, but well, a computer can do it very fast, and I will not argue. But this is an example of a minimal regular cover. It's particularly nice. Generally, if I take a less symmetric map, then the minimal regular cover is way bigger than that. It has way too many more faces. So, minimal regular covers of finite maps, so to say, minimal regular covers of maps on compact surfaces have been studied since quite several years ago in several contexts. For example, maybe some of you are familiar with the sound enfant, which starts with, well, from French, I believe it means pictures of children. And what they do is start with a picture, like this, maybe like this. They think of that as a map in the sphere, and then they take the minimal regular cover, at least in my context, and they study that. Also, Horwitz groups are particularly interesting for people in algebra, people in geometry, and several fields, and they are related to maps, regular maps with triangles 7 around every vertex. So these things all have to do with minimal regular covers. Because of the definition of map, the definitions I gave, it's obvious that we have combinatorial, geometric, algebraic, and topological tools to attack this problem of finding minimal regular covers and studying them. However, if we move to an infinite map, a map which lies in a non-compact surface, then almost nothing has been done. So a colleague and I decided to try to see whether we can find the minimal regular cover of a map, of an infinite map, and we started with the natural candidates, I guess, which are the Archimedean tilings of the Euclidean plane. So they are defined as maps in the plane that have convex faces, regular convex faces, and the symmetry group acts transitively on the vertices. Any pair of vertices can be mapped one to another by a symmetry. There are 11, 3 of them are regular, which are the tessellation by squares, by regular hexagons and equilateral triangles. And the remaining 8 have at least 2 different kinds of faces. The notation I put below is due to Roombaum, and it means that if I start at any vertex of the tessellation and I go around, then I will find faces of the sizes that are precise in there. For instance, here I have 3, 6, 3, 6, and so on. So these are 4. These are the other 4. The ones in the previous slide look easier to study than these ones, so we did start with this one, which is the easiest, and then this and this, and the remaining ones were scary at the beginning. So that was the idea, to find the minimal regular covers of the Archimedean triangles. And we found them in some way. I will say how. First, the first 3, it was done in 2011, and then the remaining 5 last year. Gordon Williams is not here, but Larnixa is. He's a co-author of that paper. And what we did is work with the groups. We did a lot of algebra, and we relied a little bit on geometry, not that much in the first paper, in the second a little bit more. But there are very few pictures of what we have, except for the minimal regular cover of the easiest one. So let me explain a little bit of what we did in the first paper. So we know that if we want to cover this, a natural cover of that may not be minimal, but will be regular, is the tessellation of the hyperbolic plane with hexagons, regular hexagons, meeting 4 around every vertex. So that will certainly cover this because every vertex has 4 faces around, and all the faces are hexagons or triangles, so I can cover with that. And the question is whether that's a minimal regular cover or not. We figure out that it's not. We still have to take the quotient of that tessellation by 2 relations. One of them is that one, whatever that means, but it's some algebraic constraint. But what it means is you take a string of 5 hexagons. Notice that every vertex belongs to 4, so you have to be careful to take the next one. And whenever you do that, you close it into a loop. So all around the tessellation in the hyperbolic plane. And a second relation says if you have now a belt of this kind, a zigzag of hexagons, you do the same. You identify the first and the 7th one as a loop. So you do that all around the hyperbolic tessellation, and you get the minimal regular cover.
Can you just say again what minimum means? I'm sorry.
So any other regular cover of my map will cover the minimum.
Oh.
That's what minimum means.
Could you say again what regular means?
Regular is, I take a flag, so that's a triangle consisting of the natural decomposition of the face. That flag can be mapped to any other flag of the map by an automorphism. In this case, I can think by an isomorph. So, okay, for that tessellation, I have some pictures that illustrate more or less what is going on. Still, they didn't tell us that much. I will go later to that. But for the other tilings, we got a lot of algebra, a lot of relations that looked this big in terms of the generator, some of them. So I felt like we finished the homework assignment. We didn't understand what that was about. So in order to know a little bit more, we attacked one of the natural questions about that. So I have minimal regular covers of these Archimedean tessellations described algebraically. I can think of them as quotients of some tessellations of the hyperbolic plane, but they are non-trivial quotients. And I would like to know what surface is that for each of them. So that's the question that started this group of people working in the Loch Ness Monster. And well, the answer has to be the Loch Ness Monster because the title is not very good. Right? So I will just briefly recall some things on surfaces. I will not give proper definitions, I will try to avoid it. But I would rather give the idea. So genus means adding handles, right? The genus of a surface. I will think of the amount of handles it has. So it can have finitely many, or you can put, well, if you have enough space, infinitely many handles, and that will be the genus. On the other hand, the ends of a surface, well, they have a complicated definition. The idea is not that complicated. You take a surface, you can take out a disk of it, and send about the boundary of the disk to infinity. And that's the idea of how an end works. So the set of ends is not just a set, they have a natural topology with the set. I would rather not talk much about it, but you can think that you are not taking closed sets, but yes, you are taking away points only, and then sending them to infinity. But you can take a sequence converging to one point and sending that to infinity, so there will be a sequence of ends converging to one. So that can happen. Not in this talk. So it is known that when compact surfaces have no ends, there's no way to go to infinity. The Euclidean plane, well, there's only one way to go to infinity. You can just think of it of an infinite tube, and you cut at the bottom and glue something in there. So that's a plane, and you can go to infinity in only one way. The cylinder has two ends, and so on. So just for curiosity, it is known that the space of ends of a surface is isomorphic to a subset of the Cantor set. So it cannot be that big. It cannot have intervals.
Closed subset, right?
True. Closed subset. Thanks. So now, I remind that if we want to classify compact surfaces, then the only thing we need is the genus. The genus gives us which topological surface we are talking about. However, in non-compact topological surfaces, that's not the case. We do need the genus. We do need the space of ends, and also we need a subset of this space, well, a subspace of the ends that are carrying infinite genus. So that means it's not the same to have this end, or this end with one or two handles, than to have these kind of ends where handles are going to infinity. So I need the subspace of the ends, the space of ends of this type. And finally, I will define the Loch Ness Monster. Well, I will define it. It's been there quite some time. It's a unique surface that has only one end and infinite genus. So I can construct it, for example, taking a torus, attaching another torus, and infinitely many. Probably that's the idea of why. There are several pictures of that. You can think of taking the Euclidean plane and having a handle on each coordinate with integer coordinates, each point with integer coordinates. And there are a lot of them. So, well, this is the theorem I was talking about. We figure out that the minimal regular cover of all Archimedean tessellations, of all non-regular Archimedean tessellations, lie on the Loch Ness Monster. And to prove that, well, we need to show two things, right? It has only one end, and it has infinite ends. This is the complicated part of the talk, at least for me, but maybe you are smarter than me in geometry, and feel free to ask for details if you want to, but I'll try not to get into very hard technicalities. So first, in the paper with Mark Mixer and Gordon Williams, we found out that the automorphism group of the minimal regular cover of any of our tessellations is virtually abelian in words of Ferran. So that means that it has a finite index subgroup isomorphic to z to the n for some n greater or equal than 2. So that was known. It was also known before that that same group if we have a group acting on a surface co-compactly and properly discontinuously, then the object called the Cayley graph, well, any of the objects called Cayley graphs have only one end. So now I have trouble because I decided not to define what that is. The Cayley graph of a group with a given generating set is a graph that has as many elements as a group, so it will have as many vertices as elements as a group, so it will be an infinite graph, and it will have edges there, it will be connected, so we can also think of how many ways does that graph goes to infinity. That would be the space of ends of that graph. I would rather not define that properly. So what this lemma says is that any Cayley graph that we construct of such a group that is virtually abelian and acts on a surface nicely has only one end. And finally, we prove that what did we prove? We have that the automorphism group of the minimal regular covers of these tessellations is virtually abelian. And then if it's virtually abelian and it acts in the way it acts, then its Cayley graphs have only one end. And finally, it was also known that the space of ends of such groups coincides with the space of ends of the surface where it acts properly discontinuously and co-compactly. So putting together some previous results, we only need to find them. We got that the underlying surface of the minimal regular cover of any of our Archimedean tilings has only one end. And there really we didn't do much work other than finding the results that were already known. And we were halfway through. So it remains to prove that it has infinite genus, right? And to prove that it has infinite genus, it's enough to prove that it has positive genus. Because the first thing we notice is that the automorphism group, because the faces of a map are disks, and it acts transitively on flags, particularly in faces. Well, you take the closure of a face and it's compact, and you can take any of them to any other, so it acts co-compactly, and it's also easy to see that it acts properly discontinuously, always. So that means that if I have a handle in there, the handle is compact somehow, I can cut it out, and I can take it around, I can move it around because of this co-compact and properly discontinuous action. So it's enough to find one handle to get infinitely many handles in there. By the way, well, and here we are using that we know that it already has one end, right? So it's an infinite surface. So, second thing we need, whenever a map on the Euclidean plane has two different types of faces, then there will appear some branch points necessarily, right? Because the faces of the regular cover will all have the same size, and that size will be bigger than the small size, the size of the small faces in the map. So that induces branch points. So for instance, if I take this tessellation of the plane, you know that there is a regular cover. There will be branch points, but not just one, there will be a full lattice of branch points, right? One per each small face in the map. And those are the ingredients I need. Now we suppose that the minimal regular cover that has only one end doesn't have handles, so it has genus 0. That means it's homeomorphic to the plane. Then I start with the tiling in my plane. I have the minimal regular cover in something that looks like the plane, topologically at least. And then we just use basic topological arguments. So we find a closed curve in R2 that has branch points inside and outside of this cover. Then we look at the pre-image of this curve. It's a union, disjoint union of infinitely many such curves. But it happens that if I look to the connected component of one of them, the projection is 1-to-1. And there's branch points inside and outside. We remember our topology of undergraduate studies, and we get to a contradiction, so that means it has infinite elements. So that's a sketch of the proof. From there we get that the genus is positive, and therefore it's infinite. So then the minimal regular cover is indeed the only surface with only one end and infinite genus. That is the Loch Ness Monster. And this has an interesting consequence. We attacked the Archimedean tilings because we already studied them in an algebraic way. However, we never used the transitivity on vertices. What we used was the branch points and some other things that happen for every periodic tiling of the plane that has at least two different kinds of faces. And there are infinitely many of those. Archimedean tilings there are only 8 if I take away the regular ones. Periodic tilings with those properties, there are infinitely many. So this theorem was way stronger than we aimed for, and it says that we know the surface where the minimal regular cover of essentially all periodic tilings of the plane live. Also, we tried using more the singularities of each tiling. So we took the tessellation 3636, the one that I used as example along the top, and we used particularly its group, the gluings that I said before, and we got to a proof of the same argument, but not using these theorems on Cayley graphs and group actions that are very strong for what we needed, just going to the texture of these tessellations. And well, we got proofs that show some geometric and topological features that the big proof I showed doesn't do. So we got some pictures. Not that many, but some, and that's good. So before concluding, I want to say that there are still some open questions. As I said at the beginning, I work on regular maps. And for those who live in uncompact surfaces, there has been very little studies. In particular, we don't know which topological surfaces of infinite type allow regular maps. We only know that the space of ends has to have only one end, two ends, or it should be the Cantor set, nothing in between. But we don't know if there are regular maps in any of those except the Loch Ness Monster. Another question is, what about the tessellations of the Euclidean plane that do not allow two linearly independent translations? Those are the ones that we know by the result I just explained. But the others we don't know. It would be nice to know. And finally, any question about this, go to Ferran. If I think of the surfaces of these minimal regular covers now geometrically, after all they are quotients of hyperbolic tessellations, so we can recover the metric easily from there. What about the Teichmuller spaces? Are they the same? So, just to conclude, I want to say that, in the work that we did, there was maps on surfaces, actions on groups on surfaces, topology of Cayley graphs, topology of surfaces, and group theory, and for that, well, we acknowledge the Loch Ness Monster, and thank you everybody.
That was fast. So, are there any questions? Please.
Yes. I have two questions actually. The first one is how you get these abelian groups inside the automorphism group. The lemma you mentioned in
Okay. So essentially it goes like this. Let's say that we have the easy tessellation.
Can you turn the lights on?
Sure.
Just for the moment.
So we know the group of the minimal regular cover of this object, and we know the way in which it acts in the tessellation. And more than in the tessellation, I'm concerned the action on the flags. So for instance, I take the action on that flag over there. What we do is we find an element of that group, of the minimal regular cover, mapping this flag to this one, and a different element mapping this flag to this one. So then I take their powers, and I do the same for a flag here. It will map it to some translate and to some other translate. And then I take quotient by that group, and it gives me that the action has to be in a finite set of flags, and therefore it has finite index. That's how we do it.
And you get to Z2 that way, right?
Oh no, here you get Z4. You have one set in this direction, another one in this direction, and two others for the triangles. Depending on each map, we will get bigger exponents here.
Second question, please.
Yes, you get translation structure structure on the Loch Ness Monster, right?
Hyperbolic.
Test construction?
No, so far hyperbolic.
Because this is finite cover of, you have a branch cover of Euclidean tiling.
Oh yeah, well you can pull the structure, the flat structure from the plane as well.
Yes, and this is the same hyperbolic surfaces, that much?
That's my question.
Oh no, it was modular hyperbolic. And with the dimensional space?
No, well the general question is you get a bunch of hyperbolic surfaces,
Yes.
and that's probably a question for you. There are several Teichmüller spaces associated to, it depends on your point of view, the Teichmüller space you get. So the question I had, if all these surfaces naturally lived in the same quasi-conformal deformation of something.
You can even ask, are they the same surface? Conformally the same?
I
And
don't
you do not know?
I don't know.
Your first question was about, your first question had to do with regular maps on non-compact surfaces, right?
Yes.
And you said, you know that, you said something, you know,
There's this theorem, what else was it?
Which
Schwarzman, yes, I think that one. That says that if a group acts co-compactly and properly discontinuously in an infinite type surface, then the surface must have, well, the space of ends must be only one end, well, it can be compact, of course, or it has two ends, or the space of ends must be the Cantor space. And all these maps need that.
It's a mixture between Schwarzmiller and Stalin's.
yeah.
Yeah, can you visualize any of these Loch Ness Monster covers? I mean, draw the tiles on a Loch Ness Monster.
Yes, well, I can't yet, but it would be nice to have something. So, the guess of some of my colleagues is that the minimal regular cover of this one can be visualized in R4, for instance. So this Z4 would act like translations. After all, what we work on, that we, I mean Ferran and the other people in the team, is that there's a set of 4 hexagons. Oops. That are the fundamental region under the quotient by this. So we can take that, it will probably be embedded nicely in R4 and then translate by that. That's the idea, we haven't done it. And the same would be true for the others, just the dimension would increase. Up to 30, 20.
You'll never get dimension 3 there.
No, but you're all even. Because always we need a translation, well, two linearly independent translations for each flow orbit. So it's always here. And greater or equal than 4.